going right along with navigating the periodic table and understanding the properties of elements would be our Bohr models and valence electrons. So as we talked about families, you also saw a lot of notes about valence electrons and outer shell electrons listed under the properties for each group. So, taking a look at what we're going to learn today, the Bohr model is going to help us understand what our valence electrons are, how those electrons are placed around the atom. And then you're going to be able to tell me what are valence electrons. So flashing back to the subatomic particles we talked about day 1 of this unit, we're going to look at our protons, neutrons, and electrons, where they are and what their charge is. So we know that our protons and neutrons are both found in the nucleus. All right, and then our electrons are found outside of the nucleus, outside of the nucleus. And then when we look at the charge of these particles, protons, remember P for proton, P for positive, also that T in proton should remind you that a little plus sign. All right, neutrons, think of neutral, so there's no charge, and then electrons, negative. Think of that L, turn it sideways, you've got a negative sign. So protons positive, neutrons neutral, and electrons are negative. Those electrons exist outside of our nucleus. So the Bohr model is essentially a way of illustrating what an atom looked like, with its protons here in the middle and its electrons floating around and neutrons contributing to mass. All right, so when we look at our Bohr model, we show that those electrons exist at specific energy levels. Currently, we have our quantum model that shows where our electrons exist in way more specificity, way more detail and accuracy. However, our Bohr model does apply to our first 18 elements, and so it's a good way for us to get an understanding of how those electrons are placed and what our valence electrons mean. So electrons only exist at levels, not in between the levels. So when we look at this diagram on the right side, energy levels or shells are these circles, all right? And so the number of shells tells you what period that element is on. So for example, if we were to look at argon on your periodic table, what period is it in? Remember, periods go left to right. It's in period 3. So therefore, argon would have 3 shells or 3 energy levels. All right, so when we draw a Bohr model, electrons fill each shell before going on to the next shell. All right, so starting from the inside out, each shell can hold 8 electrons except for the first shell. The first shell only fits 2. So it's 2, and then every shell out from that holds 8. All right, so 2, 8, 8, 8. So first shell, second shell, third shell, fourth shell. So if we look back here, notice that our first shell only held 2 electrons. Then our next shell held 8 electrons. All right, and so you only put on there how many you need. So here's our 8 electrons in the second shell. And then for this atom, I only have 14 electrons. So that's why you only see 4 on the outside, is because I didn't need all 8. But the max that each shell can hold is 2 and then 8, 8, 8 on out until you fill up your atom. So let's take a look at the Bohr model. So that first shell, or the lowest energy level, again has 2 electrons. The second can hold 8. And in this example, the third only has 4 because that's how many's there. However, it can also hold 8. That's the max. Once I would fill it up, all right, then I would have to go to the next shell. Again, the Bohr model only works for elements 1 through 18, and we are looking at the Bohr models just so that we can get a visual of electrons. So visual of electrons is why this is important. All right, you do not need to know how to draw the Bohr model, but it will help you understand valence electrons. Let's take a look at an example of argon's Bohr model. So we know that argon, if we look on a periodic table, has 18 protons. All right, so if it has 18 protons and I want to illustrate the number of electrons, well, we know it's neutral, so I also have 18 electrons. So notice here on our first ring, we know that our first ring can only hold 2 electrons. So here's those 2 electrons. I have 18 to place. I've only placed 2, so I've still got to keep going. Next ring, I can put all 8 on there, right? Because 2 plus 8 is 10. So far I've only placed 10 electrons. All right? So keep going. I've got to go to the next ring because now this one's full. And I've got 2, 4, 6, 8. All right. So 2 plus 8 plus 8 equals 18. I have illustrated argon. All right. So now you can see where that first ring only holds 2. And then the next one's going to hold up to 8 before you have to move on to the next shell. So let's take a look at an example and do it from scratch. So here I have an element of sulfur. Sulfur has an atomic number of 16, which tells me I have 16 protons. So in here in the middle, that box is representing your nucleus. So I have 16 protons. I have a mass of 32. Well, 32 minus 16 gives me 16 neutrons. That is my mass minus my protons equals neutrons. All right. Now I need to place my electrons on my energy levels outside of my nucleus. All right. This is neutral atom that I'm dealing with here. I don't see any charges. So if I have 16 protons, I also have 16 electrons. So on the first shell, I can place how many? I can place 2. 1, 2. All right. I'm not at 16 yet, so I'm not done. But the first shell is full, so I need to go to the second shell. All right? 3, 4, 5, 6, 7, 8, 9, 10. I have placed 10 electrons now. All right? 2 on that center ring, and then 8 on the middle ring. But I only have 10, so I have to keep going until I get to 16. So I'm going to go to the next ring since the middle one's full. So then I have 11, 12, 13, 14, 15, 16. There's my 16 electrons. That's how a Bohr model works. It's showing you where those electrons are placed on their energy levels. So I have 1, 2, 3, 4, 5, 6 outermost electrons. All right, 1, 2, 3, 4, 5, 6. All right, that outer shell is not full. All right, you do not have to fill it up. Those are just empty seats. Imagine them as empty seats in the classroom, right? I could have put another one here and another one here, but if I don't have students for those desks, right, the desks just stay empty. Same thing here. If there's not an electron to put in that energy level, then it just stays empty. So let's look at 2 more examples here. Next, I have carbon, atomic number 6. So that's my 6 protons. I have a mass number of 12, so 12 minus 6 gives me 6 neutrons. All right, and then I'm going to place my electrons around my atom. First shell can only hold 2. Remember, 1, 2. And then 3, 4, 5, 6. All right, and I've placed all of my electrons. That's it. All right, that's all you have to do. The next one, let's look at oxygen here. Atomic number of 8. So I have 8 protons. And then a mass number of 16. So 16 minus 8 gives me 8 neutrons. All right, these just so happen to be the same. They may differ, all right? But you have 8 protons, 8 neutrons. Since this is neutral, I also have 8 electrons because I had 8 protons. They have to be balanced. So let's place our electrons in our Bohr model. First circle, first energy level, we only have 2 electrons, right? That's the most it can hold, and then it's full. Just imagine like a little cup, all right? First one's a little cup, and then the rest of them are big cups, all right? So first we have a 2-ounce cup, and then we have all 8-ounce cups. And so imagine you've got a water pitcher, and you pour it in here. Once that one's full, now I can pour into the 8-ounce and the 8-ounce, and you keep going. Once one cup's full, you go to the next. So filled up my first energy level. I've got 2 electrons. Well, I need a total of 8. So 3, 4, 5, 6, 7, 8. All 8 electrons are placed. All right, that's how we fill out the Bohr model. So we're going to take a pause here and just practice illustrating our electrons and their energy levels using the Bohr model sheet in your packet. Please remember that the first shell holds 2, and then you go to the second shell, which can hold 8. Once your second shell is full, then you will move on to your third shell. All right, so you're working your way outward. Now let's take our Bohr models and make a connection back to how our elements are sorted into groups or families, their columns, based on their chemical properties. So, what determines these properties? Since we said we're going to make a connection between this and the Bohr models, we can assume that our electrons determine these properties, but more specifically, our valence electrons. So valence electrons are those electrons that you saw in the outermost shell of your Bohr models. All right? So elements exist in the same group because they act the same chemically based on their number of valence electrons. So elements in the same group have the same number of valence electrons. All right? Valence electrons are your outermost electrons. So group 1 has 1 valence electron. So for example, if we look at lithium, all right, we know that lithium has 3 electrons. Up here is lithium. All right, 3 electrons. So when I draw my Bohr model of lithium, here's my first shell, here's my second shell, and I'm going to place my electrons. Well, lithium has 3, as we just said, so 1, 2. That shell's full, so I need to go to the second shell, 3. So how many electrons are on your valence shell, or the outermost shell? Only 1. So you will see this happen with everything in group 1. All right, all of group 1 has only 1 valence electron. Let's look at another example. Let's look at sodium in group 1. All right, so here's sodium, Na. So I have Na with how many electrons? 11. So I need to draw 11 total electrons around sodium in our Bohr model. So my circles are a little crooked, but here's sodium. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That shell's full, so I need to go to the next one, 11. So again, my outermost circle is right here, and I have 1 valence electron on that. All right, group 2. If we look at all the atoms in group 2, group 2 is going to have 2 valence electrons. So let's look at beryllium, for example. We have Be, and then here's my first shell and my second shell. All right, so drawing those electrons, I have 4 electrons, 1, 2. That shell's full, so I have to go to the next one, 3, 4. All right, how many valence electrons are there? How many are on the outermost shell? 1, 2 electrons on the outermost shell. So we're going to see this trend continue as we work along our A group elements. All right, so remember that A group is your group 1, 2, and then 3, 4, 5, 6, 7, 8. So group 1 had 1 valence electron, group 2 has 2, group 13 has 3. All right, so if you notice right here, what's the second letter in or second number in 13? 3. Group 14 has 4. Group 15 has 5. Group 16, 6. Group 17, 7. And group 18, 8 valence electrons. All right, so again, 1, 2, 3, 4, 5, 6, 7, 8. All right, that's how many valence electrons each of those groups have. So they're grouped together based on their valence electrons. There is one exception, all right, one exception, which is helium. All right, helium only has 2, but it's in group 18. So let's look at why. Here is helium's Bohr model. So I have He, and helium only has 2 electrons to place in a Bohr model. So drawing the first level of helium, we know that the first level can hold 2 electrons. Well, look, helium, there's my 2 electrons, and I'm done. It only has 1 shell. Is that outer shell full? Yes, this shell is full. All right, well, let's compare that to neon. So here's our neon Bohr model, and then our first shell. And our first shell can hold how many? 2. 1, 2. Well, neon has 10 left to that I need to place in total. So I've got 8 more to place, so I need a second shell. So here's shell number 2, and I've got 1, 2, 3, 4, 5, 6, 7, 8. So now I have a total of 10 electrons, and guess what? Look at my outer shell. Can I fit any more there? No, my outer shell is full. So what do these have in common? Helium and neon both have full outer shells. All right, and because their outer shells are full, they can't hold any more electrons. So that is what group 18 has in common. All of group 18 has a full outer shell. All right, everything in group 18 has 8 valence electrons because their outer shell is full, except for helium, whose outer shell is full with just 2 electrons. Then when we look at our transition metals can have 1 or 2 valence electrons. It kind of varies. We will always be given that. I will never ask you the number of valence electrons a certain element in the transition metals have. You will always be given. So transition metals vary 1 or 2 valence electrons, and so do the lanthanides and actinides. Remember, those come out of your transition metals. So those, just like transition metals, have 1 or 2 valence electrons. So if we look at this all together, here you see 1, 2, 3, 4, 5, 6, 7, 8. All right, and then here's our groups in the middle that have 1 or 2 that don't really follow a trend. All right, notice here, this is the second letter or second number in their group number. All right, so group 13 has only 3 valence electrons. Group 14 has 4, 15, 5, 16, 6, 17, 7, and then 18 has 8. So let's take a look at your periodic table. All right, I want you to go to the group numbers up here, and I want you to box in or highlight, if you have a highlighter, box in, however works best for you, this second number in your group, group 13, all right, group 14, group 15, 16, 17, 18, all right? So that should remind you, look at that second number, and that is your number of valence electrons. So again, you get your total number of electrons from your atomic number. All right, so atomic number equals total electrons. All right, but the group number equals valence electrons. Valence electrons are those outermost or outer shell of electrons. So why does all of this matter? Well, knowing our valence electrons helps us to write our Lewis dot structures for particular atoms. So Lewis dot structures help us to illustrate those valence electrons that we just looked at in our Bohr models, right? We don't want to have to draw a Bohr model every time that we want to show valence electrons. And as we said, the Bohr models only work through elements 1 through 18, so we need a way of representing and illustrating the valence electrons on all of our different atoms. So that's when we have our Lewis dot structures. So I'll give you a second to write down these steps for Lewis dot structures. So step 1, writing your chemical symbol, so your abbreviation for the element that you're working with. Determine the number of valence electrons, which we know is based off of your group number. And then using that number, you are going to place a dot for each electron around the chemical symbol. As we are placing those dots, you need to put 1 dot on each side. Underline this, highlight it. 1 dot per side until all 4 sides are occupied. Then we can go back and double up if you have more than 4 valence electrons. All right, so let's look at some examples and understand what that means. So if I look here at boron, find boron on your periodic table. So let's take a look here at the first example. We've got boron. So step 1 tells you to write your chemical symbol. Well, that's written for us. And so step 2 is determine the number of valence electrons. So let's zoom in here on boron, element 5. All right, valence electrons comes from our group number. Well, it's group number 13, and so I know I have 3 valence electrons. So I'm going to go back here, and I look, and step 3 says to place 1 dot on each side until all 4 sides are occupied. All right, so 1, 2, 3. All right, I don't have any more, so all I need to place is 3. All right, you have 4 sides, place them around until you occupy all the sides. So 3 dots, and I'm done. That's all there is to it. That's your Lewis dot structure. All right, let's look at calcium, the next one, Ca. So let's go to our periodic table and locate calcium. Over here on the left side, number 20. So what is my group number? Group number 2. So how many valence electrons do I have? I have 2 valence electrons. So I need to put 1 on each side. 1, 2, and I'm done. All right, so when it says to put 1 on each side until all sides are full, it means that calcium cannot look like this. That is a big no-no. All right, boron over here can't look like this. Big no-no. Because each electron gets a side to itself until we run out of spaces. So think about you in the classroom. You all have a desk to yourself right now, and I wouldn't double you up until I ran out of desk, all right? So think about the electrons are in COVID times. They don't want to be beside anybody. They're trying to stay socially distanced until there's no more room left, right? There's only 4 sides, so eventually they're going to have to start sharing. So let's look at an example of that. Let's look at nitrogen, N. Go to our periodic table, and let's locate nitrogen over here. All right, so nitrogen, element number 7, and it is in group 15. So I have 5 valence electrons. So let's take a look at what that looks like. 1, 2, 3, 4. Now all 4 sides are filled, so what do? I'm going to have to go back and double up, right? So there's my 5th one. All right, so only 1 side is doubled up. 1, 2, 3, 4, 5. And I had to double up on that 5th one. Last example, let's look at helium here. So find helium on your periodic table. It's over here in group 18. But wait a minute, what do we say about helium? Does it have 8 valence electrons? How can it have 8 valence electrons if it only has 2 total electrons? So remember, helium is your rule breaker with 2 valence electrons. Remember, it's full with 2, so that's why it's in group 18. So let's go back over here and draw our symbol for helium. We just said it has how many valence electrons? 2. So 1, 2, and helium is done. All right. Let's look at one more example. Let's pick another one. Let's look at fluorine. All right. So let's look at fluorine. We'll do an example here. Fluorine, that was supposed to be a highlighter, not a pen. Fluorine has how many valence electrons? 7. All right, look at that second number in the group number. Fluorine has 7 valence electrons. So let's go over here. Step 1 is to write our symbol. So I have a F, and then we said it has 7 valence electrons. So 1 on each side. 1, 2, 3, 4, 5, 6, 7. And fluorine's done. All right, so that is how many valence electrons fluorine would have. Again, it doesn't matter which side you start on or which side you double up. Over here with nitrogen, I could have doubled up at the bottom instead of the top, as long as only 1 side was doubled up, and there is a total of 5. It does not matter which side you start on or where you end at. It just matters that you represent it with the 4 sides not doubled up until you are out of room and have to double up. Think they're socially distanced electrons.